Hey everybody, this is Larry. This is day 13 of the July Leetcode Day Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's poem. Today I do feel a little bit better. Thank you for people who wished me well. Should drink more water though. Actually a little bit dehydrated, just ran a couple of miles today. Not too fast, just chilling. But yeah, we'll see what happens. But today, let's take a look at, well, today's poem. 2410. Maximum matching of players with trainers. Okay, so you're given 0 index of integer array players, where players sub I represent the ability of the ith player. Okay, and then you have trainers who are the training capacity of the j trainer. The ith player can match with j trainer if the player's ability is less than or equal to. Return the maximum number of matchings between players and trainers that satisfy these conditions. And of course, this is 10 to the 5th. So in case you're wondering, you could do something like n squared, right? Or n times m or p times t, whatever you want to call it. How would you do it? I think for me, honestly, there are only a couple of ideas, right? I mean, I think in the general sense, without thinking too much about it, you may think, say, the Hungarian algorithm or bipartite matching or something like that. But of course, those algorithms are n to the cube, roughly speaking, right? So that's going to be too slow. We have 10 to the 5th. Instead, it is a little bit of a hint, right? If you know that you need to do it, or handle p and t is 10 to the 5th, then the worst you can even think about is n log n or p log t or some variation of those for this problem, right? It's not always great to work backwards like this, but this is some part of the complexity analysis, or at least maybe not complexity analysis per se yet, but at least feasibility analysis, right? If it takes you, 10 days for it to run, then maybe we should at least give an honest attempt to solve it in a faster way, regardless of whether that solution exists or not, right? Okay. And of course, in real life, you may say that you don't need the exact correct algorithm, in the sense that maybe an approximation algorithm is good enough. But in any case, now we're talking about another topic. Okay, so here, I think the way that I sometimes think about these problems is that when you have an n log n thing, it is very hard to do anything other than greedy. Maybe it doesn't have to be always greedy in the sense that greedy might not be a huge component of it, but, well, I mean, it is just some sort of greedy idea that enables things to be true. And also for this one, another thing that I think I talked about last week or maybe 2 weeks ago now, time flies, is that first thing I would do is I ask myself, does order matter? And for this problem, it does not. And there is a very reasonable, I want to say natural ordering, but maybe it's just an ordering, right? Which is to say in a sorting order. Maybe sometimes it makes sense to have it one way or the other, like from smallest to largest or largest to smallest, depending on the problem. But for now, let's just say that we can sort. And the sorting does allow us to kind of play around with this structure that we just create by sorting, right? Okay. And then the question is, okay, let's say now that we've sorted, then maybe there is going to be some idea of the 2 pointers algorithm, right? And then here is that, okay, let's say you have a 4. I think it is a little bit tricky to formulate the greedy idea precisely, right? I mean, anyone can come up with a greedy algorithm, but you want not just a greedy algorithm, but you want the correct greedy algorithm, right? And with that, it often requires a little bit of a proof, and that is sometimes a little bit tricky. And for how would I think about this? The way that I would think about this is maybe 2 ideas, right? Or 1 or 2 similar but distinct ideas that may deal with each other. One is that, okay, let's say, because we're players and trainers, right? That means that we have to do one of 2 things. We have to iterate through the trainers or iterate through the players. We probably have to do one. I mean, technically speaking, you have to iterate through both, but in the sense that not at the same time, right? You may have to iterate through trainers, but after that, or after you process players, right? Or the other way around, where you iterate through players, but only after you process trainers in some way. Of course, binary search may be, sorry, I gave the spoiler. I mean, sorting is some sort of pre-processing anyway, right? Okay. And then the question is, okay, let's say we iterate through players. What does that mean? What does it mean in a greedy way? Well, let's say we're doing the player 4. That means that we want the weakest, if you will, the smallest number trainer that match. And that's fine, right? I think that makes sense in a greedy sense, because if you choose anything bigger, then you can use the exchange argument or the swap argument, if you want to call it that, where, you know, it can lead to a more suboptimal answer. Or you could say it leads to a better answer if you always swap them. And I'm going to give you the structure of a proof. I think you can kind of do, you could kind of, it's not, you could kind of do it like exhaustively is the way that I think about it, assuming that it generalizes from, well, just like a few numbers, right? Let's say you have players, you go to some, you know, CD, and let's say that these are sorted, right? Because we already sorted them. Then now we want to say we want to match A with C, and match. All right, let's actually do it by contradiction, right? Or you know, I don't know, let's just say we want to match A with D and C with B, right? Or B with C, I guess more precisely. Well, the sort of exchange argument that you want to do here is that, or maybe it's the other way around. I always forget how I want to say this. Well, okay, let's do it the other way. Let's just say A with C, A with D, right? Let's say we want to, what do we, let's say that we want to swap them and it will give us a better answer. I think that's the way that you would prove by contradiction with this exchange thing. Is that, okay, let's say we match this, and then you could say that we want to say, by swapping, it will give us a better answer. Something like that. Also, just to be honest, this is not super rigorous. It's just kind of, you know, greedy proofs are kind of hard for me. So I don't know. But these are kind of the ideas that I would think about in terms of kind of proofs, right? It's something along these lines. And then that means that, okay, well, and the idea here is just to kind of, and then just exhaustive thing, right? Because now you have really only two possible scenarios. You have B is less than C, in which we have the same matching count, or B is greater than C. By definition, A has to be less than D, but B can be less than C or greater than C. Then now this is contradiction, right? This does not give us a better answer. This assumes, of course, just to be clear, that this already matches, and these already matches if A is less than C and B is less than D, where the relationship between B and C is not defined. But of course, in either of these cases, you can also say that A is less than B, right? Because of it is sorted, and this is C is less than D. Then by transitive property in both directions, A is less than D, right? No matter, yeah, because, yeah, right? Yeah. So that's kind of the idea behind this proof, and this allows you to actually even do a sorting type thing, maybe. But I think that's right. Let me know in the comments if I'm really wrong on this. It's been a while since I've done a random proof this way, but I think that makes sense, right? I mean, I think technically speaking, you have to also prove the other thing of you have to also prove that swapping into it only gives you a better answer. But in any case, I feel like we've done, you know, the ideas. Let me know in the comments if you disagree or whatever. But yeah, and then now we said that we want to sort it, but we also want to remove stuff. So I'm a little bit lazy. The way that I would do it is put one of them into, in my case, a sorted list. But you can put it in like I don't know. I guess in Python maybe sorted list is the easiest. But I imagine that you can write your own binary search. Balanced binary search tree, and that'll give you the log n thing as well, right? So yeah, SL is equal to sorted list trainers, right? And then now for P and players, we can find. I am just curious right now. I mean, I think with sorted, it makes sense. I'm wondering whether the sorting of P is needed, or do we always just greedy? Would that ever make sense? Or would that ever give us a different answer? The answer is yes. But can it give you a worse answer? That I don't think so, but maybe I'm wrong on that one actually. But that's why I'm curious. Well, anyway, yeah. So then we do it as bisect left P, right? We have index is equal to this. If index is less than length of SL, then we remove one. We made one match, and we remove it. So SL. I think just remove SL of index, and then that's it. So all in all, pretty okay. Hopefully I didn't make a silly mistake. Pretty slow though. And I know why it is just very slow. The reason is because I was a little bit late. I think this makes sense if we don't sort it. Or this could be a solution if we don't sort it. Let me just run it real quick because I am curious. Yeah. But the reason why this is still a little bit slow, or this is slow, is because if you sort one of them, then you don't need to do this. But if you sort both of them, as we did, then we can just do the 2 pointers algorithm, right? Because if players is already sorted, then if players is let me step back a second. The reason why we don't need to sort P is because, as we said, we process trainers and then we just get the smallest one next to it, and it works, right? But if we do sort it, then we can do the 2 pointers. And the reason the 2 pointers works is that because we sort both of them, then that means that the trainers will only increment, or like it'll be strictly to the right? And because it's strictly to the right, you can discard numbers that are smaller than the current P, because if the number is smaller than the current P, you would not need to no numbers in P is going to be smaller than that number, right? Yeah. So that means that, okay, and maybe sort, maybe the way that you can also write in a cleaner, I don't know if it's cleaner, but just put it in a queue, because I like queues. So then now while length Q is greater than 0 and Q of 0 is less than P, then Q dot pop left. Otherwise, then now if length Q is greater than 0, then the invariant is that Q length is this, and then we have Q dot left, and then count increment by 1, and that is good, right? So yeah, some ideas, and of course you could even go faster by just not using a deck or queue or whatever. Just sort, and then now you have like a tree T index thing is equal to 0, and then just write it this way. So that, you know, as you can see, there are a lot of ways to do it, right? And maybe we can even convert this to T. Right, so a lot of optimization, a lot of things. I think I had some coffee earlier by accident because I was eating coffee candy. I thought it was just coffee flavored candy, but maybe it is actually coffee. So maybe there is some caffeine in it, and I made some mistakes. But and that's why I'm solving in 4 different ways. Also, a little bit make up for yesterday, I suppose. for yesterday's lackluster video. But that'll be slightly faster, but I don't know. I can't imagine it changed too much. But actually, it changed quite a bit, but not whatever. Anyway, so these are all things you can do, and they're all the same complexity. Even though maybe I should have gone over a little bit more. One of them is, I mean, yeah, it is some variation of p log p t plus p log p plus t log t, and some variation of some of them could be linear. For example, you have p plus t log or p log t plus t log t, or something like that. There's a couple of variations of it depending on which version. This one though is p log p plus t log t, and yeah, that's all I have for this one. That's all I have for today. Let me know what you think. Thanks for watching, and yeah, stay good, stay healthy to your mental health. I'll see y'all later and take care. Bye bye.